Hello folks and welcome back. So let's go ahead and continue with our studies. In the previous three sections, we understood how to evaluate the capacitance of a capacitor. We understood how to combine capacitors in series and parallel, and we understood that there is a notion of energy associated with a capacitor. Now in this section, we're essentially going to understand how capacitors can relate to situations where you have dielectrics being used inside the capacitor. Now, what is a dielectric? A dielectric is basically a non-conducting material. And people actually did experiments with dielectrics, and they found that when they inserted a non-conducting dielectric material between the plates of a capacitor, something nice and interesting happened. Namely, the panel on the left shows a simple air-filled capacitor before any dielectric material is inserted between the plates of the capacitor. The panel on the right shows what happens when a dielectric, for example, like rubber or glass or wax paper or mica or porcelain, is inserted between the plates of the capacitor. Now you see that for the panel on the left, we have a larger electric field between the plates of the capacitor. The insertion of the dielectric between the plates of the capacitor has indeed reduced the electric field between the plates of the capacitor. Now, what does that do to the capacitance? It basically means that if the electric field between the plates of the capacitor is originally given by E0, and you reduce that electric field by a certain proportional value given by E0 divided by kappa, that becomes your new electric field, then the bottom line is that by reducing the electric field between the plates of the capacitor, you have in fact reduced the voltage across the plates of the capacitor in the configuration shown on the right lower panel. Now, why is that desirable? It is desirable because the distance between the plates is not changed, and the voltage is just the electric field times the distance. And therefore, it basically means that the voltage between the plates of the capacitor in the right figure is actually reduced by a factor of kappa, and therefore, since the capacitance is just equal to the charge divided by the voltage, it basically means that the capacitance has been increased by that same factor. Now, people actually did experiments on such situations where dielectrics have been inserted between the plates of the capacitor and actually found that the voltage between the plates of the capacitor indeed is reduced. Now, this factor of kappa is called the dielectric constant, and each different type of dielectric material will have a different dielectric constant. Some materials, which are of course non-conducting materials, all dielectrics are non-conducting materials. Some materials which are non-conducting, like mica or paper or indeed porcelain, will have actually a very large dielectric constant, which basically means that it's beneficial to insert those materials between the plates of a capacitor, because by doing so you are actually increasing the capacitance of the capacitor, and in doing so you are creating a situation where the capacitor can hold a larger amount of charge. So that is the point of inserting dielectric materials between the plates of the capacitor. Now, if you imagine that you have a parallel plate capacitor, then before the dielectric is introduced, the capacitance is just given by epsilon naught A over D, but we have seen that introducing the dielectric between the plates of the capacitor will actually increase the capacitance by a factor of kappa. So the final capacitance of this capacitor with the dielectric inserted is just given by kappa times epsilon naught times A divided by D. At least that's the case for the simple situation where you have a parallel plate capacitor. Now, you may well ask another type of question, namely that if you reduce the distance between the two plates, can you not increase the capacitance, and is that not a better way of increasing the capacitance? The answer is that yes, you could do that and increase your capacitance, but that also reduces the amount of voltage you can put on the capacitor, because it basically means that you have uh, the possibility of dielectric breakdown taking place at smaller voltages. So we realize that the better way to increase the capacitance of a capacitor is to keep the distance between the plates the same, however, to go ahead and put this sort of what we've shown as a green dielectric slug between the plates of the capacitor. What does it do? Now notice that inserting the dielectric between the plates of the capacitor does not change the charge on the capacitor. However, because the capacitance has increased and capacitance is equal to charge divided by voltage, it basically means that the voltage between the two plates has decreased. And because the voltage is decreased by that factor of kappa, which is the dielectric constant, it basically means that the voltage is equal to electric field times the distance between the plates. Therefore, we can conclude that if the voltage is decreased by a factor of kappa, then the electric field between the two plates is also decreased by a factor of kappa. This gives us our important insight that you obtain the electric field E0 in this situation before the dielectric is inserted, and you obtain the result that the electric field after the dielectric is inserted is just given by E, which is equal to E0 divided by kappa. Okay? So that's the important insight that we have gained. And we can, of course, reinforce that insight with what is written on this next transparency, which basically just says that by inserting a dielectric between the plates of a capacitor with a capacitance C0, you are actually increasing the capacitance, and that is equivalent to, indeed, reducing the voltage. And since the distance between the plates is unchanged, the charge on the capacitors is unchanged, that is equivalent to, indeed, reducing the electric field between the plates of the capacitor. Now we can always go ahead and evaluate the potential energy, but now realize that the capacitance has increased. The electric field is indeed the electric field that we have in the newer configuration, and we can therefore write the energy stored in the capacitor as being equal to this factor out here times the area of the capacitor times the distance between the two plates. So for a parallel plate capacitor, the area of the capacitor times the distance between the two plates is just equal to the volume, and this tells us that this expression out here corresponds to the energy density associated with an electric field permeating a region which has a dielectric constant kappa. So this gives us the energy density associated with the electric field when the electric field actually permeates a region that has a dielectric with a dielectric constant given by kappa. So with this important insight, we're now ready to go ahead and solve some interesting problems. So this first problem essentially tells us to initially imagine that this conducting slab is not present. Therefore, we have a conductor in the left panel on the top with an area A, which carries a positive charge, and the blue conductor at the bottom of the left panel, which has the same area A. These two conductors are separated by a distance which is given by this D out here. And therefore, we can actually say that we have a simple parallel plate capacitor which is air-filled, which has an area A and a distance between the two plates given by D. Now this is all by way of state setting, so I'll go ahead and now erase the things that I drew and point out to you that now we're going to go ahead and imagine that a metallic slug or a metallic slab is inserted between the two plates. So focus on the left panel, please, and you can actually see that this metallic slab with a thickness of A has been introduced smack dab between the two plates. The question asked of us is to find the capacitance in this new configuration. Now what I want you all to do is essentially improve your intuition so that you can actually realize that the configuration in the left figure is exactly the same as the configuration in the right figure. How do you go ahead and improve your understanding of that? The answer is that let's go ahead and imagine, if we like, that I can white out certain portions of the metallic slab that has been introduced. So imagine, if you like, that I white out this portion of the metallic slab, and from the other side I will also white out some portion of the metallic slab. Okay, now that I've whited out those portions, it is now easy to actually see that this metallic slab with the little portions whited out and carved out is essentially looking like a simple plate out here, a simple conducting plate out here with a conducting wire connecting them. Now it is very easy to see how the structure on the left, in the left panel, is essentially entirely equivalent to the structure in the right panel. So with this insight, I will actually now give myself the liberty of erasing some of the coloration that I did out in the left panel. And now we will exclusively focus on the right panel so that we can go ahead and evaluate the equivalent capacitance of this pair of capacitors, the upper capacitor out here and the lower capacitor out here, which are indeed, as you can see out here, connected in series. So we understand that capacitors connected in series are added reciprocally, and our first job is, of course, to evaluate the capacitance of any one of these two similar capacitors. So we say that the capacitance C of the top capacitor, which is same as the capacitance C of the bottom capacitor, is actually given by epsilon naught A divided by the distance between the plates, which is just given by D minus A over 2. So this tells us that we have the capacitance associated with any one of these capacitors, and we can now go ahead and realize that we want the net capacitance associated with two of these similar capacitors that are connected in series. And in order to do that, we realize that capacitors that are connected in series are indeed added reciprocally, and therefore we say that 1 over CEQ, where CEQ is the equivalent capacitance, is just given by D minus A over 2 divided by epsilon naught A, which is the reciprocal of the first capacitor, plus D minus A over 2 divided by epsilon naught A corresponding to the second capacitor. So this is actually equal to D minus A divided by epsilon naught times A, and this is equal to 1 over CEQ. Therefore, we realize that CEQ, the equivalent capacitance, is just equal to epsilon naught times A divided by D minus A. So this tells us how to essentially take a configuration that is given to us and recognize within it the subtly hidden pairs of capacitors, and then use our rules for series or parallel addition of capacitances to find the equivalent capacitance of the configuration. So the equivalent capacitance, or the capacitance of the panel on the left, is actually still given by CEQ, which is just epsilon naught A divided by D minus A. So with this insight, we're now ready to move onwards to the next problem. So in this next problem, we're told that we have a parallel plate capacitor with plates having square dimensions of 10 centimeters by 10 centimeters and separated by a distance of 4 millimeters. The first and second part of this problem are very simple. The first part says find the capacitance when there is no dielectric between the plates. And that is easy to do because that is just equal to epsilon naught times A divided by D. The second problem, or part B, basically says find the capacitance when the entire region between the plates is completely filled with a certain dielectric material having a dielectric constant of 2. And so we go ahead and just take the answer that we obtained in the first part and double it to obtain the capacitance in the second part. The third part is essentially quite interesting. So let's go ahead and focus on the third part. The third part is the one that is solved out here, and I will go ahead and solve it out here using this situation, this figure that is contained out here. So we want to find the capacitance of this structure, where I can draw it out a little differently by saying that we have one plate out here, we have the dielectric slug out here, and we have another plate out here. This distance is just, it's not shown very nicely, but this distance is just d over 4. And I can actually make everything to scale. So let me go ahead and make everything to scale. So here we're going to go ahead and say that we have a dielectric slug whose thickness is just given by 3d over 4, where d is the original distance between the two plates. Now, what can we say about the electric field? Notice that we're told that we have q amounts of charge placed out here, and the area of the plates is given by A. Therefore, the surface charge density sigma is just given by Q divided by A. And therefore, the electric field, the original electric field E0 between the two plates, is actually given by sigma divided by epsilon naught, which is actually equal to Q divided by epsilon naught times A. Okay? So let me write this a little better. So we say that the electric field is just equal to Q divided by epsilon naught times A. The original electric field before the dielectric is introduced. So in this region, we still have the original electric field, and that original electric field is still given by E0, which is equal to Q divided by epsilon naught times A. Now, what happens to the electric field in the region that is permeated by the dielectric with a dielectric constant of kappa? The answer is that the electric field gets shrunk by that factor of kappa, and so we have a smaller electric field in this region. And so the electric field in this region is just given by E0 divided by kappa, which is given by Q divided by kappa times epsilon naught times A in the denominator. Okay? So we now have a very clear understanding of the electric fields both in the vacuum region and in the region that is filled with the dielectric. So we can now go ahead and evaluate the potential difference between the two plates of this capacitor. And this potential difference is actually equal to the electric field in the air region or the vacuum region, which is given by Q divided by epsilon naught A, times the distance of that region, which is just given by D over 4. The voltage is actually equal to electric field times the distance, especially for this parallel plate situation. But we have a further voltage in the dielectric. So we take the electric field in the dielectric, which is just given by Q divided by kappa times epsilon naught times A, multiplied by the thickness of the dielectric, which is just given by 3 times D over 4. Okay, so now we can go ahead and factorize. So we do so. So we realize that this is just equal to Q times D divided by epsilon naught times A, and we take the remaining factors inside the bracket as being 1 over 4 plus 3 times kappa over 4. Okay? So then we can go ahead and write this as Q times D divided by epsilon naught times A times kappa plus 3 over 4 kappa. Okay? This is the voltage across the plates of the capacitor, and we can therefore say that the capacitance CEQ, or the equivalent capacitance of this configuration, is just equal to Q divided by whatever the voltage is. And that is actually equal to epsilon naught times A divided by D times 4 kappa divided by kappa plus 3. Okay, so this tells us how to obtain the equivalent capacitance in this lower panel out here, where the capacitor is only partially filled with the dielectric and the rest of the capacitor is filled with air. So this region is the air region, and this region out here is the dielectric region. Okay? So with this, we've understood how to solve slightly more complicated problems, but let me go ahead and show you all a different take on this problem, and many students, in fact, prefer this different take on the problem. So, look at this situation. Here, you have a parallel plate capacitor, namely this plate and this plate, and some fraction of this parallel plate capacitor is filled with dielectric. If we had to make this problem exactly analogous to the previous problem, we would say that that fraction F is equal to 3 over 4, so that 3/4 of the distance between the plates is filled with this dielectric with dielectric constant kappa, and 1/4 of the distance between the plates is filled with air. Okay? We now realize that if we slip in a thin metallic sheet out here and then go ahead and amplify that metallic sheet so that it looks like two plates that are connected with a wire, we have essentially gone ahead and turned the configuration shown on the left into a pair of capacitors, each of which has a certain capacitance that is easy to evaluate. So let's go ahead and do exactly that. So we realize that for the capacitor on the top, we're taking this distance just to remain concordant with the previous problem. We're taking this distance to be 3d over 4, and we're taking this distance to be d over 4. Okay, then we can say that the capacitance C1 is just equal to, it's a parallel plate capacitor that is entirely 100% filled with dielectric having a dielectric constant kappa. So we can say that C1 is just equal to kappa times epsilon naught times the area of the plates, which is A, divided by 3d over 4, which is the distance between the plates for C1. For C2, we can go ahead and say that C2 is exactly equal to epsilon naught A divided by the distance between the plates, but that distance is just given by d over 4. So we obtain C1 is equal to kappa times epsilon naught times A divided by 3d over 4. And we obtain C2 is equal to epsilon naught times A divided by d over 4. Okay? With this understanding, we realize that the configuration on the left is entirely equivalent to the configuration on the right, and the configuration on the right indicates that we have two capacitors that are connected in series, and we've already gone ahead and obtained the capacitance of each of those two capacitors. So we can go ahead and say that we want to now add the two capacitors in series, which means that we do 1 over CEQ. In other words, we add them reciprocally, which is equal to 1 over C1 plus 1 over C2. So this is equal to 3d over 4. I'm sorry, let me go ahead and erase this off. So we obtain 3d over 4 divided by kappa epsilon naught A plus d over 4 divided by epsilon naught A. And we can go ahead and simplify this because we can take d over epsilon naught A outside, and inside the bracket what remains behind is 3 over 4 kappa plus 1 over 4, and we can go ahead and do that addition of fractions. So we actually obtain this as being equal to d divided by epsilon naught A, and we have 3 plus kappa divided by 4 kappa. And remember that this is just 1 over CEQ, so we actually have to go ahead and set things right by obtaining the reciprocal, and so we obtain CEQ as being just equal to epsilon naught A over D times 4 kappa divided by 3 plus kappa. Notice that the answer that we've obtained out here by making the simple analogy of the configuration on the left to an analogous configuration of two series capacitors or two capacitors in series is so simple that you can actually go ahead and do it very easily. And in fact, to some extent, this is the strategy that I would urge students to indeed adopt. So we see now how to solve for rather complicated problems by basically identifying the equivalent capacitors in series or in parallel associated with this situation. Now let's go ahead and focus on this other problem. Notice that in this other problem, we have a situation where we have an upper plate with dimensions a times b. It's a rectangular plate, and a lower plate with, again, with dimensions a times b. However, the dielectric does not go all the way through between the two plates. In other words, this amount of distance has dielectric between the plates, and this amount of distance, which is just a minus x, has no dielectric between the plates. So the question is, how can we go ahead and extract from this situation an analogous situation associated with capacitors, maybe in series or maybe in parallel, and actually obtain a simple answer? What we're going to do, the solution is of course shown to you out here, but what we're going to do is essentially do a little bit of drawing that will make the problem more apparent in the next transparency. So in the next transparency, we're going to go ahead and say that this situation is entirely equivalent to a situation where I have a smaller plate. How much smaller plate? The answer is I cut this plate up and I cut this lower plate up also. And I have a plate, a smaller plate. This distance is still b, but this distance is x for this plate. And I have a lower plate also having the same shape, namely this distance is x and the other dimension is b. And between this plate, we are indeed going ahead and putting our dielectric slab. So this distance is x as I wrote down, but I should have erased this guy out here. So let me go ahead and draw this again. So this distance is given by x, all right? And between the plates that I've chosen right now, I have a dielectric slab with a dielectric constant kappa. Notice that this dielectric slab completely fills the distance between the plates. However, I have this remaining part of the plates which I also have to consider, so I draw another plate out here, and for this plate, this distance is b, and this distance is given by a minus x. Now this portion out here is nothing but an air-filled capacitor, if I want to think about it this way. So I've gone ahead and split or broken up these two plates, but of course they're indeed one and the same conductor out here. And so to make them one and the same conductor out here, I go ahead and connect them by a conducting wire. Likewise, the lower plates are also connected by a conducting wire like so. So what do you see now? You see that you've essentially formed a pair of parallel plate capacitors, and these two capacitors are indeed in parallel. And so we will actually go ahead and say that for the capacitor on the left, we have a capacitance given by C1, which is equal to kappa, because it's filled with dielectric, times epsilon naught, times the area of this plate out here, which is just given by b times x, divided by the distance between the plates, which is indeed d. And we have a second capacitor, and the plate area for this capacitor is just b times a minus x within brackets. So I obtain the capacitance C2 for the capacitor on the right as being equal to epsilon naught times b times a minus x, the whole thing in brackets, divided by d. So we can actually go ahead and say that we have two capacitors, and now these two capacitors indeed are connected by one and the same metal wire, so they effectively, the upper plates act like one and the same connected plate. So by connecting them with the upper conducting wire like this, we've essentially ensured that they're similar to the two plates being joined. Likewise, by connecting the lower two plates by a conducting wire like this, we made sure that the lower two plates effectively behave like one and the same conductor. So we made the configuration that we've just drawn equivalent to the configuration that we have on the left. Notice that the configuration on the right shows us two capacitors that are connected in parallel, and capacitors that are connected in parallel add arithmetically. So we obtain CEQ as being equal to C1 plus C2, and this is actually equal to kappa times epsilon naught times B times X divided by D plus epsilon naught times B times A minus X inside brackets divided by D. The denominator for these two fractions is the same, and indeed I can obtain epsilon naught times B divided by D times A plus kappa minus 1. Let me do this. A plus kappa minus 1 times X. So with this understanding, I have obtained a very simple form for the equivalent capacitance associated with this capacitor. So I've gone ahead and split the capacitor shown on the left, which only has dielectric jutting partways into it, into one capacitor which has a dielectric completely filling it, and for which I can actually obtain a very simple formula for its capacitance, and another capacitor which is entirely air-filled, and therefore I can also obtain a very simple formula for its capacitance. And I'd urge you all to essentially realize how we recognize the presence of these parallel plate capacitors, or these two capacitors that are in parallel, and how in the previous problem we recognized how the two capacitors are in series. So with this understanding, let's go ahead and briefly answer the next part of the question, which basically says that if this dielectric can slide in a frictionless fashion, what would it want to do? In other words, would it feel a force that drags it into the plates, or would it actually feel a force of repulsion that wants to push it out of the plates? Now, we're not going to do it in a super sophisticated fashion, but I can actually tell you that you can obtain the energy or the potential energy associated with this configuration as being equal to half of Q squared divided by C, where C in fact is CEQ, the equivalent capacitance. And if you're put to it and asked to evaluate the force, you can actually say that the force is just equal to minus du by dx. Notice that this expression for CEQ is written in terms of x, and therefore you can indeed differentiate it if you're required to do so. But we can essentially on intuitive grounds decide what would happen in this situation, because realize that when the dielectric completely goes into the space between the slabs, between the plates, when the dielectric completely fills the capacitor, then you have a situation where the capacitance is indeed increased, the charge is unchanged, and therefore you have the largest value of capacitance and therefore the lowest value of potential energy. Notice that the potential energy when the charge is a constant is proportional to the reciprocal of the equivalent capacitance, and the equivalent capacitance achieves its largest value when the dielectric completely fills the region between the two conducting plates. Therefore, the potential energy reaches its lowest value when the slab is fully inside the capacitor, and this tells us that the slab is energetically favored, or chooses to actually go fully inside the capacitor. In other words, imagine standing at the top of of a hill and wanting to run downwards. That is an energetically favorable situation, and you would naturally do it. So in an analogous way, when the slab is partially out of the capacitor or the slab is fully out of the capacitor, that results in higher potential energy compared to when the slab is completely inside the capacitor. And so the slab finds it energetically favorable to be pulled into the capacitor. And that's the solution for the part B of the problem that we were two-part problem that we were given on the previous transparency. So at least at an intuitive level, you understand how to obtain the answer to this question. With this said, we can actually go ahead and solve the problem mathematically if we so wanted, and we've essentially completed our understanding of dielectrics and how they are to be used in various circumstances and how we can find the equivalent capacitance in such situations. So with that, I will thank you for your attention and look forward to seeing you in the next unit. Thank you and see you all later. Thanks a lot. Bye-bye.